Welcome to the first lab lecture of Service Systems Design and Planning course. In this lecture, we will apply data envelopment analysis on Mid-Atlantic bus lines case. Mid-Atlantic is a first-class express bus service operating between the major coastal cities from Philadelphia to Jacksonville. Mid-Atlantic established franchises in these cities, and some of these franchises complain about inadequate profits while others are pleased. In this case study, we will identify inefficient terminals and make recommendations for them. This table shows the amounts of ticket and freight sales in addition to the labor hours and facility dollars for a typical day of each terminal. First, we should identify the inputs and outputs in order to apply data envelopment analysis. As these correspond to the sales amounts, these can be classified as outputs, and these are the inputs for the LPs that will be used for data envelopment analysis. Let me start with writing the LP model for the first terminal. As I told, we have two inputs for each terminal. One of them is labor hours, and we will use V1 as the coefficient for this input, and the other one is facility cost, and we will use V2 for this input. And we have two outputs. One of them is ticket sales, and we will use U1 as the coefficient for this output. And the other output is freight sales, and we will use U2 for this output. This is terminal or depot 1. Okay, now using these, let's write the LP model. Let me use this table as well. Okay. Now we need to maximize the efficiency of depot 1, where we express efficiency as the weighted sum of out 700 U1 plus 300 U2. So we should add first the input constraints. These 40 V1 plus 500 V2 should be 1. And for depot 1, we should write the efficiency ratio constraint. 700 U1 plus 300 U2 minus 40 V1 plus 500 V2 should be less than or equal to 0. And now let's transfer this model to Excel. Okay, this is our input Excel. Let me insert some empty lines here. Variables. We have 2 inputs and 2 outputs, so we should include 2 coefficients for outputs and 2 coefficients for inputs. And these are the cells for their values. Okay, for each depot, we should add a constraint as the efficiency ratio of each depot should be less than or equal to 1. So suppose that the left-hand side of the constraint is provided here. This is the operator column, and this column corresponds to the right-hand side. Okay, what is the left-hand side? In the left-hand side, we multiply the coefficient of output with the corresponding output for each output and take the sum of them, and then subtract the sum of inputs multiplied by their coefficients. Okay, and in order to reuse this expression, we should add dollars to the coefficient cells. Okay, this is the left-hand side. As you know, our operator is less than or equal to, and right-hand side is 0. Now we can reuse this. Okay. Let me correct this part. Okay, now we have an input constraint as well, and in this LP we are evaluating depot 1. So let me indicate this with red color. So I will use the input values of this depot. Okay, and the left-hand side is the weighted sum of inputs. Okay, the constraint should be quality constraint, and don't forget right-hand side. Okay, let me write like this. Okay, right-hand side should be 1. Constraints are ready. Now we should include the objective function. Let me correct these cells. Okay, objective function. In the objective function, we should multiply each output value with the corresponding coefficient and take the sum of these. Okay, so if you are running this model with another depot, we should change the values of these cells. Next, we should construct the LP model. The objective is given in this cell, and it is a maximization problem, and variables are provided here. Okay, and these variables are assumed to be non-negative. And now I can add my constraints. As I told before, I can insert all less than or equal to constraints together. So the left-hand side is this one. It is less than or equal to constraint, and the right-hand side is given here. Okay, I have one more constraint. It is the input constraint. This should be equality,
and the right-hand side is given here. Okay, I don't need to do anything with this tab, and I should select LP as the solver. Next, I can solve the model. As you see here, we have found an optimal objective function value of 1. It means that this depot is an efficient unit. In the online lecture, we will continue with other depots.